there are lots of different ways to represent lines in 2 dimensions. We're going to cover 5 of those different ways in this video. That seems a bit crazy. 5 different ways to express the equation of a line in 2 dimensions. Slope y-intercept form, vector form, parametric form, symmetric form, and Cartesian form. Sounds like a lot, and it is a bit crazy, but we're going to talk a little bit about each one, how to find each one, and also why we might have so many different equations for lines. So let's start off with what we know. Slope y-intercept form. We know that's just equal to y equals mx plus b. This is really the only equation of the line most of us have probably encountered up until this point. So I just have an equation line, an example line here, y equals negative 2/3 x minus 4. And I've graphed that line right here on this axis. Just assume that each block is 1 unit. So that's our regular run-of-the-mill equation of a line that we're used to using. Now, in this course, we've talked a lot about vectors, and we know how to do some fancy stuff with vectors, dot product, cross product, things like that. And we've also learned about vectors in 2 and 3 dimensions, and possibly even in the future extend it to more dimensions. So it would be nice to be able to express this same line in terms of vectors instead of just as this sort of equation, because it allows us to do some things with that. So if we think about how we could possibly express this line as a vector, let's think about this. I'm going to choose a point on the line. I'm going to choose this point right here. So this point right here would be negative 3 and 6. And say we were starting at that point. How could we get to another point on the line with a vector? Well, for example, if we want to get to this point here, we could choose a vector of 3 over and 2 down. So that vector would look like this, 3 over, and the components, the x components would be 3 and the y component would be 2. And we can sort of generate this point here by using that vector. Now, we give that vector a special name. We call that a direction vector. So if we start at this point, negative 3, 6, and we apply this vector here, we can get to another point. And if we apply this vector here and then another one of those vectors there, like we double that vector, we can get to this point here. And if we triple it, we would be able to get to this point here. So we could basically generate a line by starting at a point and multiplying by a direction vector. And we could also do the same thing the other way. We can go backwards one and generate the other side of the line as well in that same way. So how would we express that mathematically? Well, for this course, we're going to call a line in vector form. The general form is just r. So we'll call this equation r. Instead of y here for our regular slope y-intercept form, let's call it r. So our equation for our line r, we can write that as our starting point, which in this case I just chose randomly. I could have chosen any point on the line, but I chose negative 3 and 6. So I'm just going to write it like that as our starting point. And to that starting point, we're going to add this vector. And that vector, remember, we're going to call it a direction vector. It has a x component of 3 and a y component of negative 2 because it goes down by 2. So 3 and negative 2. There is our direction vector. And remember, we can generate all the points in this line by just multiplying, by starting at this point and just multiplying this by different things. So I could put a 2 in front of here, or a 3 in front of here, or a 5 in front of here, just to generate all the different points on the line. So instead of using a variable x or y, because those are sort of already taken for x and y coordinates, we use t as our variable. I like to think of t as sort of time. And if we started at this point and started adding time, we would basically start generating points. At 1 second we would be here, at 2 seconds we would be here, at 3 seconds we would be here, etc. And we continue on. And we can do the same thing going the other way. T at negative 1 would bring us here, t at negative 2 would bring us here, etc. So this would be our equation of our line in vector form. And in general, the way we write this is r equals, we call our initial point or our starting point r naught, or r0. That just means like our initial point, plus t, which is our variable, times our direction vector. Notice how I've called the direction vector m. This is our direction vector. And I've called that m because it's sort of like the slope, right? It's sort of like the slope of the line, but it's actually not the slope. Notice how the slope of this line was negative 2, 3, and our direction vector is actually 3, negative 2. And if you think about that for a second and why that's the case, just look here. How do we get this? Our slope. Well, that's rise over run. So that's sort of like y over x. Whereas when we express vectors, we put the x component on top and then the y component on the bottom. So our direction vector is actually always going to just be our slope flipped. So we call our direction vector m, and we call our starting point, or our point on the line, just r naught. Okay, so those are sort of the two things that we need to know for our vector form. And again, the variable is t. Now, the t part has a special name, actually. We call that a parameter. And it's the thing that we can just make whatever value we want in order to generate that line. Sort of similar to how in this equation we had x. And whatever we make x in this equation, it'll generate different y coordinates. In this equation, if we substitute in different t values, it's going to generate different points along the line. And we usually say that t is an element of real numbers. So it can be any value, and that when it's any value, it generates all those points along the line. So this is our equation in vector form. By the way, sometimes we write this r part here as xy, because if you think about it, this x part is the top. So this negative 3 refers to the x part, the x part of the initial point, and 3 refers to the x component of the direction vector. So that's vector form. Again, this is useful because we know how to do stuff with vectors now in this course. We know how to do cross product and dot product, and now that we have this equation in vector form, we can apply some of those things to lines. The next version of our lines is called a parametric equation, and it's very closely related to a vector form. Really all it is, it's when we break up our vector form into the x and the y components. So see how this vector r, or this line r, has the components x, negative 3 plus t times 3. That's just the x component. So we would say, if we just looked at the x component for our line here, we would say x equals negative 3 plus 3t, right? Because the t gets multiplied by both the x and the y components. So plus 3t. That's our x part. And our y part is going to be 6 minus 2t. Right? So that's just looking at the x component and the y components separately. And those two equations combined are called the parametric equations of the line. So in general, the way we write that, if we just look at sort of what this original equation is, it's going to be x, and that's always going to be our x, our initial x value of the line, which in this case was negative 3, right? That was our initial x value, plus t times a, right? A is going to be the first part of the direction vector, and y is y naught, so our starting y point, plus tb. So notice how here, actually, I forgot to mention this before, a and b we're going to use to represent the direction vector. So this 3 and 2 here, going back up here, I'm going to call this direction vector AB, where A is the x component and B is the y component of that direction vector. Okay, so AB appear here, and our point, our initial point, x naught and y naught appear here. So this is the equation, the parametric equation of our line. And realize once again how we generated it is we just looked at the x components and we looked at the y components separately. So the parametric equation is actually two separate equations that generate that line. T again is the same parameter that if you plug in values for t, it's going to generate the x components of that line. And if you plug in values for t here is going to generate the y part of that line. So for example, if I made t 0, I would plug 0 into both of these equations. That goes away. That generates the point x, -3, y 6. So it's going to generate that point there. If I made t1, it's going to be -3 plus 3, which would be 0. So the x component would be 0. And then the y, if I did that, so 6 minus 2 times 1, so 6 minus 2 is 4, would bring me to that point there. So plugging in t as 1 brings me to that point there. Plugging in t as 2 would generate the x and the y coordinates of that point, etc. So it's just basically another way of looking at this vector equation. Now you might say, why is that useful? And one quick example of why that's useful is in physics. A lot of the time we like to break up the x component of motion, so how an object moves to the left and the right, and the up and down motion. We like to separate those. So the x motion and the y motion, it's useful to separate those as two separate equations. If you're familiar with physics, projectile motion is one example of that, where it's very useful to look at the x component with one equation and the y component with another equation as t sort of increases, as time increases. So anyways, that's parametric equations of a line. Next, we have symmetric equations of a line. And to think about this, let's start with our parametric equation. And really what we want to do now is we want to say, okay, this is great, but we sort of introduced this extra variable t. Can we get rid of that t somehow? And if you think about it, can we perform maybe a little bit of substitution to get rid of that t? And the answer is yes. If we isolate t in both of these equations, we should be able to substitute and basically eliminate that t. So let's do that now. I'm going to isolate t in both equations. So the first one, just looking very quickly, I can bring this to the other side and then divide by 3. So it's going to be x plus 3 over 3 is going to equal t for our first equation here, first parametric equation. And our second parametric equation is going to be y, I'm going to move the 6, so it's going to be y minus 6 over -2. So I now have two equations, both in terms of t. So in order to make a symmetric equation, I could just plug this equation into this equation, set them equal to each other since they're both equal to t. And that gets rid of the t. So I would end up with x plus 3 over 3 equals y minus 6 over -2. There is our symmetric equation. It's called symmetric because sort of the left side and the right side look very similar. One has an x and one has a y. And think about what's happening here, what these values actually are. Well, does this 3 and this -2 look familiar? If you look back, all the way back here at our direction vector, look at our direction vector, it was 3 and -2. The x part was 3, the y part was -2. So we see those numbers here again. And what about the 3 and the -6? Well, if we look back at here, we have the 3 and then, ooh, this is -3 and 6. So it actually ends up being the opposite sign of what we have here, which is sort of interesting. So our symmetric equation, our general form for a symmetric equation is x minus our initial point, which is why the sign is flipped, over a, which was the x part of our direction vector, and y minus y naught over b. So we sort of have all the x parts on one side and all the y parts on the other side, the a and the b being the direction vector. So it's useful to sort of separate the x and the y in this way. So this is just another form of the equation, and symmetric form probably is the most useful, not for itself, but actually how we can use it to go to another form of the equation. So we can actually, we've gone from parametric to symmetric, now we can go from symmetric to Cartesian, what's called the Cartesian equation of a line. And the Cartesian equation is just this basically rearranged algebraically. Cartesian's special because all we do is we have to isolate all the terms in this equation and set it equal to 0. So how could we set this whole equation equal to 0? I'm going to try just by cross multiplying first. So I'll show my algebra over here. So I'm going to cross multiply this thing. So -2, I'm going to multiply by the x and the 3. So I'm going to get -2x minus 6, and cross multiply this up, equals 3y minus 18. So I just cross multiplied basically this equation, and now I want to isolate everything. I want to get everything to one side, put 0 on the other side. So I'm going to bring this 3 to the other side, negative 2x minus 3y, and I'm also going to bring this 18 over. It's going to become positive, and then positive 18 minus 6 is going to be 12. So plus 12 equals 0. And I don't like that there's a negative sign at the beginning, so I'm just going to multiply this whole thing by negative 1. I can do that, right? Because it's not going to affect the 0 at all. So I'm going to end up with 2x plus 3y minus 12 equals 0. And that is our Cartesian one. I'm just going to copy that up here underneath where it says Cartesian. 2x plus 3y minus 12 equals 0. This is called the Cartesian equation of our line here. And the general form of that, a little bit different. So we sort of see some of these similar numbers here. Maybe you can identify sort of where these numbers are from here. They sort of look similar to these numbers from our direction vector, and we'll get to that in a second. But the general form here is ax plus by plus c equals 0. So we have this capital A and this capital B and this capital C. One thing to take note of is that the capital A and the capital B are different from our direction vector. But what I want you to think about is how they're related. How is this 2 and this 3 related to this 3 and this negative 2? Now, if you're really clever, you might see the relationship as something having to do with perpendicular lines, right? So think about it this way. What would be perpendicular to this vector? If we think back to maybe grade 9 or 10, remember to find a perpendicular line, you take the negative reciprocal, right? So you would flip these values, so from 3, negative 2 to negative 2, 3, and then make it negative. So it would end up being 2 and 3. And that's exactly what happens here. This 2 and this 3, or this A and this B, actually represent a perpendicular vector to our line. So we actually call a perpendicular vector, you might remember, a normal. And our normal, we're going to call the vector that represents the normal n, and the n is represented as A and B, capital A and capital B. So here, our normal of our line would have the components 2 and 3. So what does that mean? Well, just a quick example. If I started at 0, 0, and I graphed that vector, our normal vector, 2, 3, I'm just going to write that. Our normal vector in this case is going to be 2 and 3. If I were to sketch that, so from this point, I'm just going to go over 2, up 3, over 2, up 3, and I'm going to plot a few of these. And then if I was to take a ruler and draw that, I'm going to draw it with a dotted line just so it's distinguishable from our other line. What do you notice about those two lines? Well, they actually are perfectly perpendicular to each other. So we call this line a normal to our line. And the vector that we generate can easily be found if we know the Cartesian equation of our line, because it's just going to be the A and the B value of our Cartesian equation. Okay? So that's essentially the 5 different ways that we can express equations of line in 2 dimensions. One sort of extension here is think about which one of these equations could actually apply to 3 or more dimensions. And that's where we're going to sort of go in the next lesson. One more thing. If we had a Cartesian equation, could we go back to a slope y-intercept equation? I think we could. All you have to do is isolate the y in this equation. And just as a little check to see if we did this whole ring of equations correctly, if you did that, you should end up with this equation that we started with. All right, there we go.